For the recording, you have a quiz that opens today at midnight and closes Sunday at midnight, and your expert TA is due this Friday. Chapter 5. Okay, so this is where we left off last time. We have this electric field. It's got this equation, which is not immediately obvious what's going on. But we did want to just run some checks on it to make sure it works. Okay, and so no, I just, yeah, there we go. Okay, give me 30 seconds to draw this out again. This was A, this was X, that was R, the electric field at that point in terms of X really, K, this was Q, QX over the square root of X squared plus A squared, not the square root. This is to the 3/2. And that was in the X hat direction. Did I get the whole thing? That looks right to me. Okay. Also, I'm gonna need the chat open. Okay. So there's a few things we need to check on this because it's got a lot going on and I want to make sure it works well. So for the last one we did kind of a like, let's make sure this field isn't too big, isn't too small, kind of works. We're going to do the same thing here, checking the limiting cases. But first, of course, whenever you do a page of math and you end up with an equation, it's nice to check your units because that's quick, that's easy. That'll tell you if you went terribly wrong initially. So let's go through this. What sort of units do we expect for an electric field? Say again? Nanovolts? Coulomb. So we definitely have coulombs in there. And in fact, it's going to be a Newton per coulomb, which I think I said once 2 weeks ago. So, you know, reasonable. Volt per meter. Volt per meter also works. I just haven't told you guys what a volt is yet. I wish I could pop that up, but I can't. Okay, and so let's see if we have newtons per coulomb on the other side. What are the units of X? Meters, yeah, because it's a length. How about Q? Coulombs. Okay. How about K? There's a coulombs in it. It's a Newton meter squared per coulomb squared. And then on the bottom here, again, we have a meter, so that's a meter squared. What about A? What sort of quantity is A? Meters, perfect. Which is good because like we need meter squared. And so I'm not even gonna like bother to add that meter squared. How about X hats? It's a trick question, by the way. Nothing is the right answer because it's a unit vector. And so it doesn't have those sort of quantities. And can I ask everyone to keep their masks over the noses? I super appreciate it. Okay, now looking at this, let's start canceling things out. So I have a coulombs there, and I can't cancel out that coulombs, but I can cancel out the squareds. I have a newtons, a meters cubed on top, and on the bottom here I have a meter squared to the 3/2. And so what is a meter squared to the 3/2? Cubed. Cubed is correct. Excellent. Good exponenting, guys. And so my meters cancel out as well. And that is wonderful because now my units are correct. And so at the very least, we can say that this equation isn't wrong to start out with. Now let's start thinking how right it could be. And so I want to do this kind of the same way we did with that bar where we said, okay, well, what if the charge were all on one side? What would be, what about on the other? And that kind of give us our limits. You know, it had to be between these two bounds. So let's think about bounds. And the two quantities I want you to think about is this X and this A. So what sort of extreme situations that we might kind of understand what would happen? What sort of extreme situations would you expect where I could say, compare, that I could say something about X and A? I don't know if I said that right. I'm just going to give you the first one because I think I explained that very, very poorly. But so here's an extreme case. For example, X much less than A. Okay, what this means is that if you look at this ring, it's got a diameter, it's got a radius of A, and if X were just a little teensiest bit off, okay? So much so that you might even think X was in the center of that ring. If you're looking at a point really close to the center of that ring, what sort of electric field would you expect to see? Zero? Can we say zero? And if you can't say zero, why would you say zero? Like, what's your justification?
It's like everything's like everything would equal out. Like it's like getting everything around the ring. So like and then all would be like.
Okay, so you're saying like by symmetry.
Yeah.
So every electric field on one side will be matched by. Right. Okay. And since you're not like off in the X dimension, you're not going to see an X component really.
Yeah.
Does that, everyone feels good about that? Okay, so for this situation, we expect the electric field to be zero, to go to zero. Okay, well, the equation we have plus A squared 3/2. Let's see if that actually happens. So in this scenario, X is much less than A. So when you add X squared to A squared, what are you gonna get? Just A squared, right? Yeah. Because if X is so much smaller than A, adding X to A, that won't really affect the overall sum. Okay. So this is really A squared to the 3/2. And what is A squared to the 3/2? A cubed. Excellent. So I'm going to cancel those twos out. Okay. And now we have KQX over A cubed. And so once again, A is very large compared to X. What would X divided by A cubed go to? 0? Okay, 0 is a good answer here. Because yeah, if you take something very small divided by something very big, you get something that approaches 0. And that is good because that is what we wanted to happen. Okay, so that's one limiting case where A is very large compared to X. What might another limiting case be? The opposite. Good answer. Where maybe X is much, much more than A. Okay, let's draw a picture of that. So if X is much, much more than A, then this ring stops looking like a ring so much. And so there's X. And it sort of just starts looking like a dot, right? You get far enough away from anything, it starts looking like a dot. Now, I do want to say that we're not saying that A goes to 0. We're just saying compared to X, A is small. A is that right there. Okay, now looking at this, and this is kind of a big thing. What sort of electric field would you expect?
It's the standard like equation that we've seen before.
Awesome. Okay. And so I want the reason that I emphasize it's not that A is 0 or X is infinite. Because if X were infinite, we'd expect 0 for the electric field, right? But we're not seeing that. What we're seeing is really more just like a change in geometry. Instead of it being like this big extended ring where some parts of it cancel out, we just really see a point charge. And the equation we have for a point charge is just going to look like that, right? Where we have KQ divided by the distance from the charge squared. Okay, and so again, we'll take our equation that we started with, and we will see if it simplifies down to that. Okay, so I'm starting with that x squared plus a squared again. But now a is really small compared to x. So what am I going to end up with x squared plus a squared? X squared, perfect. And now again, I have the x squared to the 3/2. And what am I going to end up with those exponents? X cubed. And now I have kqx over x cubed. And I'm hoping everyone sees that I'm really ending up there with a 1 over x squared. And so that is a kq over x squared. And again, that's exactly what we wanted, right? Okay, so this equation not only is dimensionally consistent, it seems to match our expectations. And so that's a pretty good signal that we got it right. Okay, and I'm about to move on from this problem, but I do kind of just want to know. So I think we spent like 20 minutes on it last time. There was a lot to it. We had to think really hard. I want you to hold on to that when we start talking about potential energy and potential difference, because we're going to do this problem again, and it's going to be much simpler the next time we do it. Okay, so just refer back to this in 2 weeks. Okay, continuous charges. I think the thing I was going to ask you after this was there was a force problem that had like a continuous charge, like a blob of charge, and I was going to ask you if you guys wanted to go through it or you felt confident doing it on your own. What do you think? Whichever you like is fine. Number 13. Because we can move on. I feel you guys are making a mistake, but yes. Yes, that is the right answer. Okay. Okay, so so this one is, we're not looking at electric field, you're looking at an electric force, but we're gonna have a lot of the same ideas of how do you how do you deal with a continuous charge instead of like a point charge? And so we have one charge at the origin of this system, Q1, excellent. And we have another charge that's spread out over a rod. So we have like a rod here. And are we going to call it Q2? Yes, we're going to call it Q2. Where Q2 is uniformly distributed. And whenever you guys see uniformly distributed, just know that you're going to do some sort of density. We know that the rod is a distance, starts a distance d away from the origin. And we know the rod is of length L, capital L. And so what we want to end up with is we want to end up with the force between Q1 and Q2. So force between Q1 and Q2. That's where we're going to end up. But let's kind of go through this problem because I like the way it walks through. Okay. Both Q2, Q1. This is the force. Let me just make sure I'm right about my charges here. Point charge, Q2, direction the I'm really sorry. Let me be vague about this. Okay, so we're gonna consider a small slice of thickness dx. So there's my small slice of thickness. It's got a thickness of dx and a charge dq. Now let me ask you, if Q1 and dq are positive, there will be some force between that small little chunk and the Q1 at the origin. Will the small little chunk be pushed in the positive x direction or the negative x direction if they're both positive? Yeah, if they're both positive, will the small chunk be pushed away from Q1 or towards Q1?
Away from.
Okay, so if they're both positive, it'll be pushed in the positive x direction. What if one's negative? What if like Q1 is negative and DQ is positive? Which way will DQ be pushed? Okay, I'm not entirely sure this problem says what the charges in either one are, but that's what it is, just in case. Okay, now what we want, okay, so we're still just dealing with a small little chunk. Now I want to write an equation for the force, which we're going to call dF, that's between Q1 and DQ. Does that make sense? Okay. So in general, when I ask for an electric force, what are you guys going to tell me? What equation would you use? Yes, not KQX. What Coulomb's law? What's Coulomb's law? Perfect. KQ1 Q2 over R squared. Okay. So in general, when someone says electric force, go there first. And so for this specific thing, dF, our Q1 is a capital Q1. Our Q2 is a DQ. And now the hard thing to do is to figure out the distance between these two things. What are your initial thoughts? Like if you were going to tell me the position of DQ,
B plus L minus whoever the X position.
okay, actually, I kind of like that. I'm gonna say no, but only because I need to repeat where the origin is. Where the origin x equals 0 is right there in the center. So if we're measuring from there,
So we can just use X.
yeah, we could just use x. Does that make sense? Because x is always just measured from 0. Okay, so this is going to be x squared. Okay, so far so good. Except of course we're going to want to integrate this, right? And so when we choose different DQs, are they all going to have the same x's or are they going to have different x's? Different x's. So we need to relate DQ to x. Okay, that's fine because we're going to use the same method. We're going to use that density thing where the total charge of the rod divided by the total length will equal to the little chunk of charge over the little chunk of length. Okay, so the total charge over the total length will equal the small chunk of charge over the small chunk of length, because the density of each little part is the same as the density of the whole. Okay, and so just algebra-ing our way through there. DQ equals Q over L dx. And then if we like that, we can substitute in for DQ down here. Okay, so on the next page, I'll have DF equals K Q over X squared times Q over L dx. And I need to say Q2 here, and I need to say Q1 there. Because if you don't keep track of your subscripts, you're just a little bit doomed. Okay, everyone happy? Okay, you shouldn't be because that should be squared. And but everything else here looks great. Okay, by the way, this is part B. Okay. And now we're going to look at part C, where of course we want to just integrate. Once we have the little chunk, we're just going to integrate this thing. So the total force will be the integral of dF, or the integral of K Q1 Q2 dx over Lx squared. And let's put some limits on that. So we're integrating x. Where should we start integrating x, and where should we stop integrating? And let's go with the start. Where should we start? D, excellent. Where should we stop? D plus L. You got it. So yeah, we should start right here and we should end right there, basically. So we're going from D to D plus L. Okie dokie. And now let's start separating out our constants from our variables. K, constant or variable? Q1. Q2. Constant, because that's the total charge. L, constant. Okay, so we have 1 over x squared, right? So K, Q1, Q2 over L. We're integrating from D to D plus L, dx over x squared. Okay, that's looking pretty good. What is the integral of 1 over x squared? Shall we rewrite it? Yeah, so if I had really asked you what's the integral of x to the -2, could you tell me that one? So we add 1. We add 1. Yeah, we add 1. Like that, right? Okay, okay, good, good, good. So the answer is -1 over x. Excellent, excellent. -1 over x. Okay, this looks really great. And we plug in our limits, and I should have done this on the next line. I am going to put it down here. I'm going to put it on the next line because I have infinite amount of digital space. Why would I do it any other way? Minus a -1 over d. And let's get through this because I don't want to just leave it. But at this point, we're just doing algebra, right? And while algebra might not be our best friend, I think we can do it. Okay, Q1, Q2 over L. And so I have D plus L minus D over D, D plus L. And my D's cancel out on top. Notice my L is also going to cancel out with that L. And I'll be left with a semi-recognizable formula, I hope. Force equals K Q1 Q2, K Q1 Q2 over D plus L. And in the positive or negative x direction, depending on what the charges of these things are, which I'm still not positive about. But does this look, oh yes, in the back. Yes, yes. D's. Does this look familiar? And if it does, from where? Coulomb's law? Okay, yeah, so definitely we got this K Q1 Q2 over distance squared. Does it maybe remind you of a problem we did on Tuesday? Yeah, because we did the electric field of a bar, right? And we ended up with like a KQ over A times D plus A or L plus A or something. And I hope no one's like super shocked that we come out with pretty much the same thing, given that an electric force is a charge times an electric field. So what if you had just figured out the electric field of that bar, you could multiply in a charge anytime you wanted to figure out the force. Okay, everyone pretty happy? Okay. Okay, given that, so the one big thing left I have to do in this chapter is draw some electric fields, which we're gonna do. But before I jump into that, are there any other problems that we need to do from the homework? And if they're not, It's totally fine if there's not. Let's draw some electric fields. Okay, electric fields. Okay, so we, oh, 18? Oh, thank you. 18 and 20.
20. Yeah, he said 20. Jason.
Okay. What was 20? Oh, yeah. So this one's pretty much the one we did on Tuesday. But we can, but let's run through it kind of quick, just because I do actually have the time today. So, no, that's A. Sorry, that's an A. That's the X direction. So we have a bar, length L. We're going to consider a chunk of it dq, length dx. We're going to want to figure out the electric field at this point. And where, let me just where is the origin? It's located at the x-axis, a distance. And I think they're telling me the origin is right there. Okay. And again, I really like the way they set this up. So let me tell you, the rod has a total charge of positive 2.2 microcoulombs. It is uniformly distributed. And so if we're looking at point P, is the electric field going to point in the positive x direction or negative x direction if the charge is positive? So do electric fields point away from positive charges or towards positive charges? Away. So we expect to see something in the positive x direction. Okay. Then what we want to do is we want to write the electric field for just that one small little chunk. And if you're going to write an electric field just in general, I say, hey guys, right, what's the equation for electric field? What would you tell me? What is the equation we have for electric fields? KQ, I like KQ. Over x squared. And I'm going to say in general r squared, but we're about to say x squared. Okay, in general, that's the equation you want to use for electric fields. It's the electric field of a point charge. Now, since we're looking for the electric field of just this one little chunk, we can consider it a point charge. So our dE would be k dq. And now r goes from the charge to the point in question. So how would you describe that distance right there in terms of maybe x, L, and A, and maybe not even L? Is that where you were? Okay, yeah. And I like that you use negative because that one definitely tripped me up. Since x equals 0 is in the middle there, that way is the negative direction. And so you definitely want to include like an A minus X right there. Okay. Now, clearly, we are about to integrate this. So we need to think if we go to different chunks on this bar, choose different DQs, is our X going to change? Or is it going to be a constant? It's going to change. Okay, so that means we need to relate X to A. And how will we do this? Could we do it the same way? Yes, good, okay, glad, excellent. Yeah, so again, we were like, hey, this bar has a uniform charge density, right? So we can still say, you know, the charge of the whole, I'm sorry, the density of the whole thing is the same as the density of any little chunk I pull out. So the charge density of the whole thing, charge per unit length, is the same as the charge density of any little point I pull out. And so dq will equal capital Q over L dx. And let me put this on the next page. So dE equals K over A minus X squared Q over L dx. Okay, and there's part B. Part C, we're going to integrate that. So the total electric field, and I'm not going to bother putting a vector because we're not really doing that, is the integral is adding up all the little parts of the field. And so we're going to add up KQL dx over A minus X squared. And I wrote it suggestively because K, Q, and L are all constants, right? So they will go outside, and we're really integrating dx over A minus X squared. Which you are all probably saying is almost the same as integrating 1 over X squared. So close, right? And in fact, I'm sure other people can do it in their heads. I cannot. I would do a U substitution and say U equals A minus X. So du equals negative dx. And see, if I did in my head, I would drop that minus sign. Is everyone happy with that? Okay. So to make that substitution, we have negative du over u squared. And that there shouldn't be a minus sign there, sorry. But once I pull it out, now there will be kq over L. The integral of 1 over X squared is negative 1 over X. So this is negative 1 over A minus X. Pulled a bit of a fast one, substituting that U back in. If anybody wants to yell about it, now is the time. It's 1 over, it's really negative 1 over U, but U is A minus X. Okay, cool. And now we need to think hard about our limits. So we're adding up all the dx's, right? Where should we start adding up dx's and where should we stop? Negative L is a good place to start. Where should we stop? 0. 0 is a perfect place to stop. So we're going from negative L to 0. I'm canceling out some minus signs. And we have KQ over L, 1 over A minus 1 over A plus L. I think that's right. Okay, good, good. And by now I'm kind of hoping you're looking at this and saying we've done this twice already. KQ over L, A plus L minus A over A plus L. And my A's cancel and my L's cancel. And we're right there at the electric field. And you were saying, wow, that looks just like this electric force that we just calculated. And of course it is, because we're still calculating, we have that bar, and here the force, we just multiplied that by another charge. And so it's quite delightful. And does that work out? I definitely went a little fast at points. But are there any questions? Yes. A minus O up right there. Okay, good. I'm glad you asked that. So what we were determining there is this yellow arrow. So yeah, so you're starting at like the outside bound, which is not a terrible thing to look at, where like you're looking at the whole thing. But yeah, as you choose different, yeah, and that's really important, because when you choose the next DQ, you know, like you're gonna have to add up all the little DQs, it's gonna change. Good question. Okay, any other questions out there? Okay, let's draw some electric fields. Okay. All right, just to refresh, the picture of the electric field is if you have some charge that you want to see what kind of electric properties it is putting out, you put a small positive chest charge around it, Q naught, and kind of map out the forces that you would expect to see. And then you take that idea and you kind of formalize it into an all over picture, where you have these lines where the direction of the lines will tell you the direction a positive charge would feel, which means your field line should go away from positive charges and towards negative charges. The density of the lines is going to tell you how strong the field is. So when they're closer together, you get a stronger field. Further apart, you get a weaker field. And that's one of the reasons why your lines always need to either start or end on a charge or go off to infinity. So I can't say, wow, this space over here looks kind of empty, let me add in an extra line right there, because that would change the density of lines in that area. Sound okay? The other thing is that if you have two charges and you want to map the field from this system of charge, you should never have lines that cross. Because what's going to happen is if you have electric field lines from two different spots, they're not going to interfere with each other so much as they're just going to add together to one overall net field. And that's what you should be seeing. And so I think this is a fine example right here of a monopole. It went fast, yes. This is a good example of a monopole. And so let's do a dipole. Let's do a positive charge over there and a negative charge over there. And so the way I usually, so if I'm faced with a situation that I haven't mapped out before, what I do is I go and I draw the field for each charge separately, and then I think about how the lines will add together. So like I know this positive charge is going to put out a field like this with the field going that way. And I know this negative charge is going to have a pretty identical field, because all monopoles have a pretty identical field, except the lines will be going towards it instead of away from it. Okay. Yes. Yes, and let's talk about those lines crossing, because that can't happen, right? We need to think about what's going to happen when this yellow line and this blue line add together. So so just like any other arrow, we're going to add it like a vector. And so we have a blue vector going up and to the right. We have a yellow vector going down and to the right. So what's going to happen to the ups and downs of this? They are going to merge into each other. And so, yeah, so if I have one going up and another one going down, the ups and downs are canceling, right? But since they're both going to the right, that's going to add together. So instead of the yellow and the blue, I would draw something like the green. Sound okay? And the same thing on the bottom here. The ups and the downs would cancel out, and I'd have the net force right there. And notice in the center there, the lines are going in the same direction. So again, they would just add together. And just so you know, you would definitely see a little bit of curvature around the edges here, where if you drew a bigger picture, like this line would eventually loop back in as this line, and this line would loop back in at that line. But these two lines, if you draw them perfectly symmetric, will still go off to infinity. Okay, did that make sense? Everyone pretty happy there? Yes.
I mean, I guess this is go for like two charges, but do test charges interfere with each other?
That I'm so glad you asked that question, because that is a question to ask. Because we wouldn't want that, right? The whole point of a test charge is we want to test something else. We don't want to test the charge itself. And so that's generally why we call it like a small positive test charge, with the emphasis on small, where it should be small enough that it won't affect the overall situation. But that is, yeah, definitely something you have to think about. Everyone kind of happy? Okie dokie. Let's really quick do two positive charges. And then I want to do a parallel plate capacitor. And then that'll be enough. Okay, so that last thing, this is called the dipole. Anything with two charges is in fact called the dipole. But this one, instead of having opposite charges, we're going to have like charges. And so again, I'm gonna start the same way because a single charge always puts out the same sort of field, this just completely symmetric radial field. Okay. But now looking at these arrows, right in between the two charges, right in the center, what's happening to those fields? Yeah, they're repelled, they're canceling out. So we're actually not gonna have anything right there. And above the charges, now we have two arrows going like that. So what way will they add together to? When you add something like this to something like this, what do you get? Yeah, something like that. So what we're really gonna see is something like that. And same thing on the bottom, they'll go down and you'll see a slight deviation as you're going around here, where all of these lines are trying to avoid each other. Okay, so that's the other dipole. Yeah, so when you bring these charges close to each other, you'll see their lines just move away. And the reason I wanted to do this one is because so now you see what happens when you put two positive charges next to each other. The sideways stuff seems to cancel out and you just get up and down stuff. But what if I put a whole bunch of positive charges next to each other? What if I did that? And let's let me draw this prettier. That's not very pretty. Let me do it like this. So what if I just put more and more of these charges together? Now each one of these charges wants to do the radial thing, right? Well, what's going to happen to all the horizontal components of these arrows? They're all going to cancel out. And we're really just going to be left with lots of vertical stuff left over, right? Like we're going to have lots of vertical stuff. Sorry, that line shouldn't be there. Same thing here, lots of vertical stuff. And if I add even more charges in, it gets more and more vertical, right? So the more charges I add along here, the more vertical I'm gonna get. And of course, on the other side, of course, I could put a line of negative charges. And so for the negative charges, do I need to worry about any horizontal stuff? All right. I should just have these lines that are going like this. And since they can't go sideways, would you consider these lines to be parallel or not parallel? Pretty parallel, right? Because they can't go side to side. So if you're looking in this region there, and if you pretend for a second that I can draw like really nice straight lines, all you would see is a bunch of straight lines, right? Okay, that means the distance between these lines is constant throughout this whole space. What does that tell you about the electric field strength across this whole space? Does it change? Evenly distributed. What about like the electric field really close to the charge versus the electric field in the center. And by really close, I mean, you know, not close enough that it's touching, but like right there. Would that matter? No, it wouldn't, because those charges, they have to be, the lines are parallel. And so it doesn't matter if you're close to one side or if you're in the middle, your electric field is going to be constant throughout this whole space. That's a big thing. And just so you know, this is called a parallel plate capacitor. And we will talk about them for an entire chapter. Okay. I am almost done here with this chapter. Let me double check that I've hit everything that I need to hit. And would you all like to ask any questions before I call it? Okay, we did charge, we did induction, we did Coulomb's law, we did the electric field, we did charge distributions, electric field lines, and we did electric dipoles. Okay, I'm good. Anybody want to ask a question about the homework? Concepts in class? Yeah, what problem was this? Question 1, part C. Okay. Really quick, that's actually a great way to finish this out. So question 1. So for question 1, just for reference, you have a penny with a mass of 2.5 grams and a charge of 3.1 nanocoulombs. And first you're asked, you know, how could you get this charge? Like what does it mean? And what they're asking is, do I just have protons in this penny? Like how do you get a positive charge? And the idea is you just have more protons than electrons. So the number of protons is more than the number of electrons. Okay. And then you're asked how many electrons were transferred in order to create the charge. So how many fewer electrons do you need for this to happen? And what you need to know there is that the charge on an electron is 1.6 times 10 to the negative 19th coulomb. And that's a cool concept because that's a quantized number. So we've split an atom, right? I got your protons, neutrons, and electrons. And we've even actually split protons up and neutrons up, but we've never split an electron. So when someone says that they pulled an electron off an object, that means that object has lost exactly 1.6 times 10 to the negative 19 coulombs. And they can't pull off half an electron. So you can't lose half that charge. You lose exactly that amount of charge. So that means if you have 3.1 times 10 to the negative 9th coulombs, you have one electron for every 1.6 times 10 to the negative 19th coulombs. And however many electrons that is, that's whatever number that is, that's the number of electrons you have. Okay, and then the question you actually asked, part C, if at most one electron is removed from any single atom, what percent of the atoms are ionized by this charging process? Okay, sure. No wonder you didn't like that part. I like the first two parts of this problem. I don't like the last. Okay, so things you need to know. We're gonna say that this penny is copper. Good. And so the atomic mass of copper. And I have it in front of me, but you'd have to go look this up. Is 63.4546. Excellent. Units per kilogram. And so if you want to know the number of AMU, atomic mass units, 63, okay, whatever. If you want to know how many okay, we have a gram. Ooh. Good. No, I think you're right. I'm just
Whatever mass the penny was divided by the atomic mass times 6.02 times 10 to the 23.
I'm gonna have you come write that on the board. Yeah, in the back. Okay, no, walk me through this really quick.
So, like, you have like moles like that.
Yeah, mole
Uh,
6.022, 23, right? Yeah. Atoms per mole, right? Okay.
And then, so you have like the mass of the penny. You divide that by the atomic mass. So like that, the 63.
Copper, okay. So over 63.56 U.
Oh yeah, sorry. And then you multiply, so you multiply that number by the mole. So that's how you get the number.
Of atoms. Okay. And then how do you convert that to grams? Let me guess. You multiply it by 1.66 times 10 to the 24th grams per atomic mass unit. Grams per mole. Okay, good. No, man, chemistry is never going to be grams per mole. And so that means we need to multiply the top by this Avogadro's number, right?
Yes.
Yeah, okay, good. No. If I had a way to cancel out parts of these questions, I would. Okay, like that. And there, I'm gonna, here's what I'm gonna say. At least my units are canceling out. Okay, and so yeah, I get around 11% after those numbers are ran.
What's that symbol next to the X?
Next to my X. There's no X up there.
6.02.
All times 10.
Times 10 to the 23rd. Yeah, actually, Anthony, if you want to put yours into chat, I'd appreciate it too. Because yeah, I feel there's probably really straightforward way of doing this. However, now that we've established I cannot do chemistry, any other questions?
Answer is 11%, right?
Well, that's just for my numbers.
Once you get the number of atoms, then you could just divide it by how many electrons.
Oh, that's a good
Yeah,
one.
yeah.
Okay.
Oh, that's what he said there. Oh,
Yeah.
Yeah, that's what
Yeah. Oh, see, that's smart. That's really smart.
Thank you, Anthony.
Anthony, yeah, Anthony wins that question. Okay, no, I like that. Mass divided by
No conversion needed.
the number of electrons. You need to like multiply, you gotta get that electron in electron mass though, right?
Because it's like, if you did from part B, you're figuring out, how many, like, you figure out how many electrons we needed, right? So
Okay.
we know 100% of them would be ionized, the number of electrons that we needed, with the same number
Yeah,
of atoms. So
Yeah.
you can find the proportion, so half of them, by dividing it, you can figure out.
that makes sense. That makes sense. That's really good. Okay, I like that. That is really interesting. Okay, but I am gonna call this, I'm gonna say thank you guys for a week. And I will see you next week. Online people, are you doing okay?
Question.
Uh-huh.
We have to print the packet for the lab.
I know you